Hey guys, so today I want to teach you about the different types of bonds, as well as how these molecules that you've learned the shape for interact with each other. Okay, so here we go. We're going to talk about polar and nonpolar bonds. So we can have covalent or ionic bonds. An ionic bond is when the electronegativity difference between two atoms is really big, above 1.7. Okay, but within covalent, when they're sharing electrons, you can have a nonpolar bond, which is low electronegativity, or a polar covalent bond. So it could be nonpolar covalent or polar covalent. And polar is kind of in between, okay, nonpolar and ionic. So again, as a reminder, electronegativity is how much an atom attracts electrons when it's bonded to another atom. Okay, so how badly does it share? If it shares really well, then it's not very polar. If it doesn't share very well, if it's very greedy, then it is polar. Okay, so if you remember, fluorine is the most electronegative element in the periodic table. And the farther away you get from fluorine, the less electronegative you are. Okay, so again, here are the differences that we talked about. Okay, I'm going to skip this slide here. Now, we can talk about the electronegativity differences between elements and calculate them, but ultimately what it does is it comes down to the shape. Okay, so if a shape is symmetrical, even if the individual bonds are polar, the polarities cancel out and the molecule becomes nonpolar. Okay, so for example, BF3 here is symmetrical. It's trigonoplanar. So even though these three individual bonds between boron and fluorine are all polar bonds, like fluorine is pretty greedy for the electrons, because they are perfectly at 120 degrees from each other and they're perfectly symmetrical, they actually cancel each other out. Okay, so this BF3 molecule acts completely nonpolar. Same thing up here with HCl. Okay, this is not symmetrical, so that polarity kind of stays in place. It doesn't get canceled out. Okay, down here for CCl4, carbon tetrachloride, you see that it's tetrahedral, and tetrahedral is a three-dimensionally symmetrical shape. It doesn't seem symmetrical two-dimensionally, but three-dimensionally it is. Okay. Now, one thing to note here on the right side is that this molecule on the far right, CH3Cl, even though it is tetrahedral and it is the angles are all evenly spread out three-dimensionally, it's not symmetrical because the outer atoms aren't the same. So note here the difference between the bottom middle molecule and the one on the right. But the point is, if it's symmetrical, the polarity cancels and the molecule becomes nonpolar. If it is not symmetrical, if it is asymmetrical, the polarities don't cancel and the molecule stays polar. Okay, so how do you know which shapes are which, like which shapes are symmetrical or not? The way, frankly, I learned this is I just remember these three bullet points on the left. And if I remember these three bullet points on the left, I remember everything that's on this slide. So basically, if something is linear, planar, or if it doesn't have any lone pairs in the central atom, it's symmetrical. Okay? And then everything else is not symmetrical. And that's all that it comes down to. Okay? So if you can remember these three bullet points on the left, top left, linear, planar, and shapes without lone pairs in the central atom are symmetrical, which means they are nonpolar. Now, why do we care about this? Differences in polarity explain why things don't mix. So, for example, if you try to mix water and oil, water is polar and oil is nonpolar. Okay? So that's why they don't mix. And this is actually really important for life because the bilipid cell membrane that every cell-based organism has is essentially functions because of this difference between polarity and lack of polarity. Okay, so it's really important for life. Water is a polar molecule, And it's called the universal solvent because it can dissolve more things than anything else that we know of. So it's the best solvent that there is. It can dissolve the greatest quantity of things. So water's called a universal solvent because of that. Now, we're talking lots about interactions, okay? So we're going to talk about these interactions here, and these interactions are called intermolecular forces, or IMF for short. When we talk about an international war, we talk about a war between different countries. The American Civil War, for example, was an intranational war, which means it was within a country. So intermolecular forces are forces of attractions, not bonds, between atoms or compounds, different compounds. Okay, not within the same compound, but different compounds or different elements. So there it is. IMFs, intermolecular forces, are force of attraction between molecules. The stronger the IMF, the higher the melting point and the higher the boiling point. Okay, so for example, solids at room temperature have stronger IMFs than liquids at room temperature. Okay, because the stronger your IMF, the more likely you are to be a solid. Okay, there are 3 types of IMFs that we're going to go over here. Dipole-dipole, which is just basic polarity. Hydrogen bonding, which is kind of a misnomer because it's not really a bond. It's just something that's super polar. And something called London dispersion. Okay, so let's go through them. If you see here, on the top 3 substances here are all ionic substances, which means they have very high melting points and very high boiling points. Okay, and their ionic substances are always a solid at room temperature. And we talked about the lattice energy of these. Okay, now what we are doing now is talking just about covalent. We're not talking about ionic. And as you can see, we have 4 different covalent molecules here, which can be a solid, liquid, or gas at room temperature, which is about 73-ish Fahrenheit. And then they have wildly different melting points and boiling points, okay? And this has to do with the IMFs, okay? So let's start getting into this a little bit more. So stronger IMFs at higher boiling points, which help us predict phases. Stronger IMFs are more polar and more likely to be water soluble. And stronger IMFs more likely to be better conductors of electricity. All right, so let's go through the first one. A dipole-dipole is just the force in between molecules because they're polar. Okay, so if you have a molecule that's polar, they're going to be partially negative and partially positive. Well, they're going to be attracted to another polar molecule because of those partial charges. Okay, and again, remember, geometry is the single most important factor. Symmetrical molecules are not polar, they are non-polar. I'm going to post this in Google Classroom for you guys to watch. I would really watch it because it's very helpful. Again here, all right, explanation of what polarity is. Molecules that are polar do not have the symmetry to cancel out the individual bonds, okay? Whether molecules that are non-polar do have that symmetry that cancels out the polarity between the bonds. All right, now I want to talk about the second force, which is called hydrogen bonding, okay? It's not really a bond, okay? It's kind of a bad name in my opinion. But hydrogen bonding is basically a superpolar molecule. And that happens when hydrogen bonds with 3 unique substances. Here they are, okay? Fluorine, oxygen, and nitrogen, or FON for short. If hydrogen is bonded to fluorine, or if hydrogen is bonded to oxygen, or if hydrogen is bonded to nitrogen, it will have a strong dipole-dipole force in between the molecules. So if you look at this picture here, you have the hydrofluoric acid here, and you see how the fluorine in one side, which is partially negative, is very attracted to the hydrogen in a different molecule, which is partially positive. Okay, that's all that the hydrogen quote-unquote bond is, a super polarity, a super strong attraction, but it's not quite like a bond just yet. Again, hydrogen bonds are super important for life. You may recognize this from biology. This is DNA. What keeps our DNA intact until the polymerase or helicase comes and breaks it up is the hydrogen bond. So here we see hydrogen and nitrogen, and then being attracted to the oxygen on the other side, and then hydrogen and nitrogen again. Okay? So if we look at this here, so look at the first two. These first two, actually the first three structures, but especially the first two, they're very similar to each other. The top one experiences hydrogen bonding because you have a hydrogen bonded to an oxygen. The second one experiences dipole-dipole because you have that sulfur and the hydrogen. The last one is nonpolar, okay, because carbon and hydrogen is a nonpolar bond. So you can see the difference in boiling points. Hydrogen bonding, the top one is 97.4, and then the boiling point just decreases, okay? Comparing here water and hydrogen sulfide, again, water experiences hydrogen bonding because of the OH. Hydrogen sulfide does not. And you can see the differences in boiling point because that hydrogen bonding makes such a big difference in how these molecules just react to nature. And then the same thing again with ammonia and phosphine. Okay, hydrogen bonding makes a big difference in their boiling points. London dispersion is the last force. It's a force that just naturally exists between all matter. So random electron motion may cause a temporary imbalance in the charge, and for a brief moment, the atoms act as if they were polar for like half a second if all the electrons are just magically found on the left side, for example, of a molecule, and then they go back to normal. But they induce the same behavior in molecules close to them. Basically, bigger atoms or molecules have more London dispersion than smaller ones because they have more electrons. I will post this in Google Classroom for you guys to see. And a quick review, dipole-dipole, okay, is any polarity that is due to the composition of the molecule, geometry being very important. Hydrogen bonding is the strongest IMF, occurs between two molecules in which hydrogen is bonded to phon. London dispersion is found in all molecules, but it is the weakest, okay? And it happens when electrons are unevenly distributed for a brief moment of time. Large molecules have more London dispersion than smaller molecules. So when you're looking at a molecule, is it made of matter? It's got London dispersion, so everything. Is it asymmetrical? If yes, it's dipole-dipole. If not, then it's nonpolar. Is hydrogen bonded to phon? If yes, it's hydrogen bonding. If no, then no hydrogen bonding present. We will get to practice going through this kind of checklist a whole lot this week. Just wanted to introduce the concept to you guys today.